Welcome to the next lecture of this series. In this lecture, we will see the DC-DC current source converters. So, we know that most of the loads of power electronics are basically voltage source loads. So, but there are also some types of loads where some of the similar to loads, there are also some electrical sources which are acting either in the constant current region or for some mode of operation of the device, or which are completely current source device. So classical example for the current sources are solar photovoltaic, fuel cell, battery, etc. Battery, at least for some range of operation, it acts in a constant current region. Fuel cell also acts as a constant current region, and solar photovoltaic for a given irradiation and temperature, it acts as a constant current source or a dependent current source. So that's why there is a need to analyze DC-DC converters for current sources. Similarly, there are some types of loads where the loads require constant current for operation. So classical example is LED lamps, then some medical devices like plasma devices, then welding applications where the voltage is very less but the current is very high, which has to be constant. So there are many types examples of loads which need constant current. So that's why the idea for DC-DC current converters comes into picture. So in this lecture we will see DC-DC current converters, and that too switch mode current converters, SMPC converters. So let's say that there is a voltage source, constant voltage source I in, which has to be connected to a load R, whose demand is that it should have a constant current I naught. So we need to add a switch. We can't add switch in series of it because we can't even momentarily open circuit a current source. So that's why we can connect in parallel. That's why this is the switch S1. So if we draw the waveform of this S1 versus time, so what you will get is that the current I naught will be, when the switch is on, the current through I naught will be 0, else it will be IN. This is IN versus 0. Let's say this is D into T switching. So if you write this and say this is the average value of the current, that is the average value of the current, average value of I naught. So I've already written the in capital, which is, you can write as average value of I naught is 1 minus D times of input current, but the input current is constant current I in. This is I in. So this I in waveform is basically chopped off, and only the portion in the D 1 minus D into T switching time goes to the load. So I naught is 1 minus D into I in. This is the basic current converter. Now there are few issues with respect to this converter. So there are a few assumptions. First assumption is that I in is a constant current source. Supplying the load requirements, load current requirements. Second one is that I naught has to be constant, because that is the assumption, and that is the reason, that is the motivation why we are going for DC-DC voltage to current converters. So we have to maintain this I naught has to be constant. To do this, we add an inductor. Why inductor? In series with in series with the load R. Why? Because the inductor will not allow sudden change in the current through it. So that's why if we add a very bulky inductor, so I should write a bulky inductor. So the load becomes like this. This is V naught. This is L. This is R. I'm writing it I naught. Instead of writing here in capital, I'll write this I naught as small. Like this. This is I naught. So average value of I naught is capital I naught. Like this. So this becomes capital I naught. So now this becomes the load side. Now we know that VL is L di by dt, or delta I naught by delta T. So as the switch is on and off, the value of the current in the load suddenly changes from 0 to I in. So this is very sharp change. So this value is increased. So this will result in huge VL drop. So this VL drop, so this huge VL drop may damage the switch or the device S1. So that's why we should have an infinite voltage source to absorb the. So we add a capacitor. So what we do is, to get rid of it, we need to have a circuit element that will absorb that ripple value, so that the voltage drop across the inductor is reduced. So we add a capacitor. But how do we add in series or parallel? We should add in parallel because we have to split the current. So that's why we should add in parallel. Add a capacitor in parallel to absorb huge delta I naught. So now the converter becomes like this. This is the switch S1, this is IN. So now this becomes the capacitor C, inductor, and the load. This is I naught. Now another serious issue happens is that when the switch S1 is on, the capacitor is short circuited, which means that very huge current will flow through this path. A very huge current will flow through this part, which will damage the switch. Damage to S1 due to short circuit of C. So we can't neglect C because we need the C to take care of the delta I naught ripples. But this capacitor will again damage the switch S1 because it will short circuited. So what we need to have it, we add another switch, and the use of that switch is to open circuit the capacitor when S1 is on. So basically, therefore S2 should be off when S1 is on. So we circuit. So basically now we'll see the valid circuit configuration. So this is the input side. Say this is the input side. This is IN. This is my thing. Inside this black box, there are a few elements like capacitor, switch S1, S2, it's a capacitor C. Now it is fixed that the inductor will be in series with the load because that is our ultimate requirement. So let's say this is the G rail, this is one rail, sorry, this is the node number 1, node number 2, this is the inductor, this is the load, this is I0, and this voltage is V0. So we'll see what are the constraints. Our constraints will be, so first in the assumption we'll add, again the assumption is, we'll add again 2 points in the assumption. Again the assumption is that L is high to filter out the current I0. Second is C should be very high. Why? Because to continue carrying the voltage, high to carry voltage required for the load. So it is sufficiently high, not very high. So the constraints are IN shouldn't be open circuited even momentarily. Second is the capacitor shouldn't be short circuited even momentarily. So this G node will be same. So this G node will be same. So basically we can't open circuit 1 to G and 2 to G can't be open circuited. So another thing is that as it's a I2 shall not be, so instead of writing I2, let I0 will not be equals to IN because it is a switch mode power converter device. So I0 will be some function of IN. So that is at least, that is switch cannot be placed, that is okay, first I'll let in terms of negative statements or negations, that is switch S1 and S2 cannot be directly placed between nodes 1 and 2. Between nodes 1 and 2. So there has to be some circuit element, say capacitor, between nodes 1 and 2. Or it can be simply short circuited. Either a short circuit should be between either there should be an element connecting 1 and 2, or either 1 and G can be short circuited and 2 and G can be short circuited. So now I'll write the possibilities. The possibilities are 1 to G and 2 to G can be short circuited momentarily. Because you can short circuit a current source, but you can't short circuit a voltage source. So if 1 and G is shorted, the capacitor should not get short. Either it should be connected to the input side, or capacitor can be connected across this side. So next is that C can be connected either between 1 to G or 2 to G, but it cannot be short circuit. But it can be short circuited. So these are the possibilities. Another possibility we can write as S1 should be S2 complement, because the need of S2 is to not allow the capacitor to be short circuited. So the capacitor has to be connected either between 1 to G or 2 to G momentarily. Everything is momentarily. So now we'll write about valid circuit phases of DC-DC. Instead of writing current source, I'll write current converter. What are the valid phases? We'll see. So one more thing, as I said, that a capacitor should be connected in parallel to consume or to absorb the sudden change in the load ripple. So the capacitor cannot be connected in series between 1 and 2. So the capacitor cannot be connected in series between 1 and 2. Means actually it can be connected, but then again 1 and G can be short circuited, 2 and G can be short circuited. So C can be connected between. So here I will shift this momentarily to this side, and I'll write here 1G, 2G and 1 and 2 momentarily. So what will happen if a capacitor is connected in series between node 1 and 2? In that case, so as the capacitor should be in parallel with the load, so 1 and G should be short circuited in that case. So what we write, if, so I'll push this down. If C is between 1 and 2, 1 and G should be short circuited. Why? Because the capacitor should be in parallel with the, always parallel with the 2 to G. That is, or I'll write on the next line, that is C should always be connected across 2 to G. This we concluded. So if we now write the valid phases, I'll write the valid phases. Phase number 1. In phase number 1, what I will do is that, let's say this is IN. I'll simply, now these phases are when there is no switch, only circuit configurations I'm writing. So I'm connecting the capacitor this in this way. The inductor is here and the load is here, and the load is connected here. This is valid because momentarily, so we have to exclude all the negations or the constraints. I think this is valid because the delta I will go, the ripple in the inductor current will be absorbed by the capacitor. The capacitor is not short circuited momentarily. The input voltage, current source is not open circuited momentarily, so it is valid. Next is phase 2 where, say, I'm short circuiting input current source momentarily, but the capacitor, there is no option with me to connect the capacitor to the load because it has to be always connected in parallel to the load. So this is the valid phase. If I write phase 3, so I'll just interchange the capacitor to this side and this short circuit to this side. So this will give me what? IN, this is C, then a short circuit, L and R. In this case, the capacitor is not connected to this rail. Which rail? Across the load. Then the capacitor can be, then the nodes 2 and G, this is G, this is 1, this is 2. If capacitor is connected between 1 and G, then 2 and G should be short circuited. So which is also valid because now, let's say initially the circuit was connected in phase 1, suddenly it changes to phase 3. In that case, so in first case, the current through the load was what? It was IN versus IC. Then in the third case, it is what? 0. IL equals to 0. So this is also a valid phase. So these are the valid phases. Now deriving the topology which gives these 3 valid ways. So similar to DC-DC boost, similar to DC-DC voltage converter, there are 3 basic switching configurations available for the above 3 phases. First is, if you just observe this C, you'll find that C is always in parallel. Just in first case it is connected to both input output, in second case it is connected to output, in third case it is connected to input. So there has to be this. Now this is what? This is 1, this is 2, this is G, this is 1, this is 2, this is G. So there has to be some switch on both the side of the capacitor, here and here. Okay, there has to be switches on both side of the capacitor. So let's say if you first combine, so circuit 1, let's say we are deriving circuit 1, so we are using phases 1 and 2. We are combining 1 and 2. At a time we are combining only 2 phases. So phase 1 says that the capacitor is connected between parallel between 1 and 2, sorry, is connected to both 1 and 2 nodes. In second phase it is connected only to this which nodes, only between 2 and G, which means that the capacitor is always connected between one node of the capacitor is always connected to the node number 2. So one switch is needed between 1 and 2 to separate phase 1 and phase 2, and the other switch should be this short circuit. So if I write like this, in this way, it will be this is S1, this is S2. So S1 S2 complementary. If S2 is on, S1 is off. So now this is node number 1, node number 2, this is G. So now what we see is that if S1 is on, S2 is off, it means that it is phase 2. So S1 S2, so 0 1 1 0, which, so here I'll write phase. If S1 is 0, S2 is on, it is phase 1. So phase 1, phase 2. This is the a table I am writing like this. This was circuit configuration 1. Let's say if I write circuit configuration 2, where I combine phases 2 and 3. Phases 2 and 3, see what is the common thing. In phases 2 and 3, actually, once the capacitor is connected between node 2G and 2NG, and in the next switching case, the capacitor is connected between node 1 and G. And so basically the difference is coming between these short circuits which you are observing here. So what to do here is, we have to have two switches there in the place of that. Then where will be the capacitor? Then there is no option for the capacitor rather than to be connected between nodes 1 and 2. So we'll connect the capacitor between nodes 1 and 2. Like this, S1, S2, the inductor and the load. So if I write S1, S2, 0 1 1 0, if S1 is 0, S2 is 1. If S2 is 1, S1 is 0, which means that the capacitor is connected between 2 and G. So between 2 and G means it is phase 3, else it is phase 2. So this is how second circuit configuration is derived. Now the final circuit configuration 3 is where I combine phases 1 and 3. See the similarity between 1 and 3. In 1 and 3, the capacitor, one node of capacitor is always connected to node number 1, and the difference lies in this short circuit. So in this place of this short circuit, I add a switch. Sorry, yeah, one switch comes in place of this short circuit, and another switch comes because there is one more difference, that here phase 3 1 and 2 are not connected, in phase 1 1 and 2 are connected. So the second switch comes here, and the capacitor is always connected to the input current source. So the circuit configuration will be like this. Here the capacitor is connected, here one switch is connected, S1, another switch is S2, then there is an inductor and the load. So S1, S2, phase 0 1 1 0. We'll see what are the valid phases. If S1 is off, S2 is on, which means that the load is short circuited. Out of 1 and 3, where the load is short circuited is in 3. So this will be 3 and this will be 1. So this I will circle to avoid the confusion that these are the valid phases. So these are the basic circuit configuration of DC-DC current converters. Now we can use the principle of the volt second balance and amp second balance for deriving the steady state. Now in in DC-DC converters we used to find the M of D, that is V0 by Vin. Now we'll find M of D as I0 by I in. This we will find. So now we'll now see the steady state analysis of circuit 1. Of the circuit 1. So circuit 1 is this. So this is the circuit configuration. This is the IN, this is IS1, this should be IS2, this is C, this is IC, this is I0. Oh, I forgot the inductor. Like this inductor should be here. This is L, this is IL, this is R, this is V0. The assumption is that here V0 is constant, because in DC-DC voltage converters the assumption was that the load current is constant. Now here in this case output voltage is constant. So here what we have to do is, this is VL plus minus, and this is VC plus minus. In circuit configuration number 1, this relation always holds. What is the relation? If you apply KVL in this loop, it will be VC equals to VL plus V0. So this will be the KVL. Similarly, so we'll now do the analysis of the waveforms, steady state waveforms of this DC-DC current converter of which is described in this circuit 1. So this is the assumption that the voltage is constant. Voltage across the load should be constant. So the current can be pulsating. So IS1 will be when the switch, so this is the duty ratio. To this duty ratio D is given, where D is the duty ratio. So if I draw like this, starting from this line, then this becomes my gate pulse 1 0. This is for S1. So for S2, it is complement. I will write it here. This is for S1, this is for S2, because they operate in the complementary fashion. This I bring it down. So we'll start with this current through the switches. So IS1 will be if IN is constant. This is also another assumption that IN is almost constant. So when S1 is on, IS1 will be on. Means the current, we are drawing only the currents through it. So when S1 is off, that time, okay, I did a mistake. So when S1 is on, the current through it is on. So I'll draw using separate color. And the current through the other switch is like this. This will be what? IS2, and this is IS1. I have drawn the simplest waveform of the current between this sources. Now I'll quickly write an equation. So that equation is, I'll solve the equation on this side. The equation is IS2 which is IC plus IL. IS2 is IC plus IL. So now I want to do the amp second balance for this. So what I will write is that IC will be IS2 minus IL. This I can write simply. So here the amplitudes are I in. So if you have a close look over the load, so V naught is constant, which also means that I load is also constant. So the average value of IL will be constant, and the inductor is very large. So that's why the waveform of I small IL will be equals to this I naught, average value of I naught. So IC was IS2 minus IL. Now we'll draw IC. So when S1 is on, S2 is off. So IS2 will be 0. So value of IC will be what? Minus I naught. So I'll draw here minus I naught when the switch S1 is on. This I'll write as minus I naught. And what is the value of the capacitor current when S2 is on? It will be IS2 minus IL, and IS2 here is I in. So it will be I in minus I naught, plus of I in minus I naught. So like this. So this value is I in minus I naught, and this waveform belongs to, I'll write here IC. Sorry for the bad choice of the color, but I don't have any option. Now let's use this violet or purple color, whatever it is called, for the voltage across the capacitor. So ICC dV by dt. So V is 1 by C integral IC dt. So means it is nothing but integration of this waveform. So integration of this waveform minus I naught will be what? It will be it will be what? So integration of minus I naught value will be a falling edge, and integration of this waveform, that is I n minus I naught, will be a rising edge. So waveform of VC will be a triangular waveform. Now we have to see that does it has any average value or not. So here in this case, if the switch S1 is on, the voltage across VC, if S1 is on and S2 is off, so in that case the voltage of VC is equals to V0 plus voltage across the inductor. And vice versa, what happens is when S2 is on, we can't determine the voltage across the capacitor because there is a current source lying there. So that's why what we'll do is we'll know that the capacitor has some average value of voltage. So it has some average value. The waveform of VL will be like this. Oh. It will be like this. This waveform belongs to VC. So this you can call it as delta VC, and this is the average value. Capital VC, or average value of VC. So this is the capacitor voltage waveform. Similarly, what you can draw the voltage for the voltage for current of the inductor is already drawn. So I naught you can already draw I naught like this. Oh. This is what this waveform belongs to I naught. The assumption is that I naught is a constant current. Because in DC-DC voltage controllers, we add a capacitor to filter out the ripples of the voltage because we want the voltage to be constant. So similarly, we assume that V0 has some average value with very less ripple content. That ripple content is governed by the series inductor. So now we'll see. So in this DC voltage converter, what we said is that the at the load side, whatever is the current ripple, we use the KCL. What we saw is that using the KCL, the ripple in the current just before the capacitor, out of that ripple flows to the capacitor and constant value of current goes to the load. Same analogy we'll be using here for the voltage ripples. So in this case, VC equals to VL plus V0. So what happens is in this case, VC has triangular waveform with some average value. So V0 should be constant. So we will take the ripple out of it. So instead of assuming that I0 is constant, I'll draw the waveform file at the last. So, or saying that just like in the DC-DC voltage converter, I assume that I load is constant. Then what I used to do is I used to find the current in the load, and then so basically the current in the capacitor, and then integrating it to find the output voltage, which is to be constant, an average value plus some ripple. That ripple can be straight line or quadratic and all so on. So similarly what we'll do is, out of this waveform of Vc, the ripple content will go to the what? It will go to the inductor. That's why this waveform I'll just bring it down like this. This waveform belongs to voltage across the inductor, where this is delta Vc or delta here, delta Vc, delta Vc. The ripple term goes here. Because V0 is constant, so I'll draw the waveform of V0. Very quickly I'll draw the waveform for V0. So I shouldn't have erased that waveform, but anyways. So this waveform belongs to V0. So this one belongs to V0. Vc is here, VL is here, and V0 is here. So this is what? This is average value of Vc. This thing, or I write in terms of arrow. So now the remaining term is I have to draw I0. So here writing this is wrong. V0 is constant in this case, not the I0. So given that you know V0, then I think you can draw I0 using the and IL is equals to I0. So what I will do is VL is L dIL by dt. So IL is 1 by L integral what? VL dt. So now if I draw the waveform of IL, it will be integration of VL. What is VL? VL is this triangle. Integration of triangle is quadratic. So in this case, it will be like this. Quadratic with falling edge. Then again it will be rising. Then again falling. Then again rising. And the current has some average value which is given by V0 by R. So this is the nature of the I0 current, having some average value. Okay, I'll redraw it. Capital I0, and this term, okay, I'll erase this. This is falling one like this. So this term, what is this? This is delta IL. So I think I have drawn all the waveforms. Now we have to do the volt second and the amp second balance. First we'll do the amp second balance. We'll do the amp second balance. What does the amp second balance say is that sigma ICT is 0. Where is IC waveform? This is the IC waveform. So minus I0 into D switching. Minus I0 into D switching plus what? I in minus I0. Minus I0 into 1 minus D into T switching is equals to 0. I'll cancel this D switching. It will be I naught D is equals to I in minus I naught into 1 minus D. Sending I naught this side, what I'll get is, or not like this, sending this I naught and this side, what I'll get is I naught in bracket D. So in this case I naught should be less than I in. This is the assumption. So that's why I in minus I naught is positive. So that's why what happens is I naught D is equals to I in minus I naught into 1 minus D. Okay, so it will be D plus 1 minus D. Yes, I am correct. Equals to I in into 1 minus D. So I naught is what? I in into 1 minus D. Therefore, M of D, which is I naught by I in, is 1 minus D here. So since 0 is less than D is less than 1, this is the buck current converter. Now if I do the volt second balance for the inductor, where is the inductor voltage? This is the inductor voltage. Similarly, this will be some area, say A1. This area will be A2, and this time will be what? T switching by 2. This will be T switching by 2. So A1 equals to A2 for amp second balance, sorry, volt second balance. A1 equals to A2. Then I will write this as A3. That is for amp second balance. What is the amp second balance? That A1 is equals to A2. So this was for circuit 1, which is the buck converter. Similarly, if we do for circuit 2, what will it be for circuit 2? Circuit 2 is this. I'll just copy this. IS2, IS1, IC, VC, VL, V0, I0, which equals to IL, I in. So let's start with the switching pulse. Then the switching pulse. This is for S1, S2, 1, 1, 0, 0. Now I just have to bring them down. So again, I start with the current IS1. Here this is I in. So I in is what? IS1 plus IC. Whenever the switch S1 is on, the current through S1 is I in minus IC, and when the switch S1 is off, then the current through it is 0. Similarly, if S2 is on, then I in equals to IC. So in this case, what we'll do is we'll let the VS2 plus minus. So here VS2 will be VL plus V0. So out of this VS2, this will be constant and this will be the ripple value. So VS2 will have an average with some ripple value. This is the KVL in this branch. So now I'll draw the waveform for V0. V0 is constant. This is the waveform for V0, which is constant. Next, I have to draw the waveform of IC. Then I can draw the waveform for VC. So first I have to write IC. So in this, from this equation, what is IC? IC is if the switch S1 is on and S2 is off, in that case IC will be equals to I0. Or say it is equals to IL. Else, if S1 is off and S2 is on, IC is equals to IN, and IN is constant. So in this case, in order to satisfy the amp-second balance, as IN is constant, so I'm here in this table I actually did a mistake. So I should draw a table like this: S1, S2. So 0, 1, 1, 0, and the phase should be 1 and 2. This is the correct table. Similarly, this 3, this should be here 3, 2, and here phase should be there. Similarly, here 3 and here 1. Here phase should come. One and 2. So in circuit 2 we'll get phases 2 and 3. So if S1 is on and S2 is off, in that case, if you want to find IC, in this circuit it is difficult to find. So first we'll see what is the valid phase when S1 is on. So when S1 was on and S2 was off, 1, 0 and 0, 1. So when S1 was on, out of phase 2 and 3, wherever if S1 is on, then it, in case input should be short circuit. So phase is 2 and 3. It is phase 2 and 3. This was as per the table. So first we have to see phase 2, then we have to see the phase 3. In phase 2, what is the capacitor current? Here IC equals to minus I0. And here what is the capacitor current? Here IC equals to I in. So in this case, in the previous case, IC in both the case was what? I naught and minus I naught and I minus I naught. So similarly, in this case, it will be minus I naught. Instead of writing here, I'll write here minus I naught. So very simple to analyze. First it was minus I naught. Then it is in. So this is in. This is minus I naught. This is waveform of what? Waveform of IC. Then VC is 1 by C integral IC dt. Again, in this case, VL has VC has some average value. So it is like this: falling edge, again rising edge, falling, rising, and falling. This waveform is VC. Again, this is delta VC, and this term is capital VC. So in this case, capital VC is the average value of VC. It is the average value of VC as per the load. And here, ideally, it should go to the ripple should be absorbed by the inductor. So if you want to see VC, or what is the voltage across the node 2 and G in the phases 2 and 3. So this is voltage V to G, and here again it is V to G, which is what? V to G is the voltage across S2. So V to G is VC and it is 0. So this is for phase 2 and this is for phase 3. We'll use this. So this V to G varies between VC and 0. So we'll draw V to G. So I'll use the orange color. What was V to G? VC and 0. So this is VC and 0. Okay, I did a mistake. Okay, VC means like this. Okay, I'll use some other color. I'll use this color. Okay, I'll use the same blue color. Like this. So doesn't it look similar to DC-DC voltage converter, where this waveform belongs to V to G or VS2, because out of the VS2 the ripple goes to, so like this. So out of VS2, for V0 it is constant. For VL, the ripple goes. So we can easily draw VL. This is VS2. Now we can draw IS2 also. What is IS2? IC and I naught. So if we draw what VL, what it will be? It will be like this. This is 0. This is VC. And by what value does it goes down? By V naught value. So this is V naught, because since this is the voltage of V naught, it is constant. V naught versus T. This waveform belongs to VL. If you know VL, you can draw IL. Now, so IL is 1 by L integral VL dt, because VL is L dIL by dt. So you can integrate it to draw the IL. So if we integrate a linear term, it will be quadratic with a falling edge. So it will be like this. If we integrate a constant term, it this is minus V naught. You can write minus V naught, and this is no need to write VC. So it will be a falling straight line like this. This is a straight line, and this is a falling curve like this. So this is VL. Sorry, this is not VL. This is IL. So IL. What is the average value of IL? It is I naught. This is I naught, and this term is what? Delta IL. So these are the waveform for this particular converter. Quickly we'll do the amp second balance. For amp second balance, that is for capacitor current. This is the area A1, this is the area A2. So A1 is minus I naught and plus I in. So it will be minus I naught into D switching plus IN into 1 minus D into T switching is what? 0. So I naught D is IN 1 minus D. Therefore M of D, which is I naught by I in, is 1 minus D by D. So what it is? It is a buck boost converter. buck boost current converter. Similarly for volt second balance, this is A3. This is A4. What is A4? A4 is V0 into 1 minus D into T switching. So that you can use to find. But in practically we don't have any current mode, any current control, any current DC converters. So we will limit our analysis only up to amp second balance and deriving the steady state transfer function between input and output current. So now quickly we will go to circuit number 3 and we'll start drawing the waveforms. So again Vs2 is VL plus V0. So V0 is constant. So we'll have the ripple term. So we'll draw the steady state waveforms. So these are the waveform of S1 and S2. Now we'll draw the waveform for IC. IC is I in minus I S1. That is, when S1 is on, and S2 is off, so IS1 becomes I0. So IC becomes average value VL, right? Now you might be having a question that why for writing the current for IC I am considering only the DC value of I0. Well, let's say the switch S1 is on, so IS1 equals to I0. So I0 I can write the instantaneous value. So why only average value? It is because the inductor is so big so that the peak ripple in the current will be neglected. So when S1 is off, what you can write as IC is that if S1 is off, VC is equals to IN plus IN. So now I'll draw the waveform for IC. So it is V in minus V0. V in minus V0, and for the other case it is okay, V in minus V0. So in this case, yeah, now we have to know the amp second balance. So the amp second balance is that for one pole. So here I did a mistake. I didn't know I0 is greater than IN or IN is greater than I0. So when S1 is off, it is straightforward that IC is plus V IN. But for S1 is on, IC is IN minus I0. So if this area is above the 0 axis, then this area has to go below 0 axis. So therefore, I0 should be greater than IN to make this area negative. So this is the assumption. This is I0 minus IN, and for other case it is IN. This is IN. This waveform belongs to IC. Now I can draw VC. VC is 1 by C integral IC dt. So negative elements are falling edge. So VC. with the average value of Vc, and this is delta Vc. This is the value of Vc. Now after Vc, we should go to the output side, that is Vs2. That is what is Vs2. So we'll write Vs2 when S1 is on, and when S1 is off. When S1 is on, the switch is open, so the voltage across S2 becomes Vc. It becomes Vc. And when S1 is off, S2 is on, voltage across it logically becomes 0. So now I am drawing Vs2. For S1 on, it is Vc. So again, and for it other case it is 0. So this waveform belongs to what? Vs2, where the average value of Vs2 this is what? Vs2. So average value of Vs2 becomes what? 1 minus d times average value of Vc, or 1 minus d into average value of Vc. This has to be valid. So out of this, the ripple value goes to the inductor, because inductor is placed in series with the resistor. This is V0. So this waveform belongs to VL, it is across the inductor. So IL is 1 by L integral VL of dt. So integration of a negative signal is a falling straight line ramp, and for a falling ramp it is falling slope like this. So this waveform belongs to I0 or IL, where this is delta IL and this average value is capital I0. So using the amp second balance, this is A1, A2, and for volt second balance, this is A3, A4. Using amp balance, second balance, for on time it is V0 minus Vin. So sorry, I0 minus In. So I0 minus In into D into T switching. plus I in into 1 minus D, T switching is 0. This gets cancelled. So if I rearrange, it will be I in minus I naught D is equals to I in into 1 minus D. If I send I in here, it will be I in D minus it is 100% into D switching plus I into 1 minus D switching. Yeah, I reverse this sign. Yeah, okay. Oh, this is D. So I minus I naught. So this becomes negative. So if I brought it here, it will be D plus 1 minus D equals to I naught D. dt gets cancelled. So I naught is I in by D. So it is a current boost converter. Current boost converter. Now one concept we'll quickly see, which is of critical capacitance. Just like for DC-DC voltage converter, the inductor current waveform was discontinuous if L is less than L critical. Similarly, the capacitor current waveform in all the three cases is triangular in nature. It will be discontinuous if Vc minimum is 0. So when Vc minimum is equals to 0, which means that average value of Vc equals to delta Vc by 2. This is the condition, and this is the waveform for discontinuity. So this is Vc versus time. This is average value of Vc average, and this is one switching time period. So you know that ICC dV by dt, so delta Vc by delta t. So what you can do is now there are three types of this thing. So let's see, IC on is C into delta Vc by d into t switching. So therefore delta Vc is IC on into T on. I like T on. It is C delta Vc by T on. So delta Vc is IC on into T on by C. And in this, and in the respective cases, we have to substitute the value of average value of Vc. That is average value of Vc, like where does it goes. So this we can substitute. So therefore average value of Vc is IC on into T on by C, which gives us C is IC on into T on by average value of Vc. This is the critical capacitance. So for the DC-DC current buck converter, here average value of Vc equals to V naught. For DC-DC buck boost current converter, this was VC. So what is to happen is VS2 was V0, and what is VS2? 1 minus D into VC is equals to V0. Similarly, for DC-DC boost current converter, same ratio holds, that is 1 minus D into VC, which is equals to V0. So therefore, this is C critical. C critical is, there are three cases. For circuit 1, what is IC on? So for circuit 1, we'll write I0. So capital I0 into D to T switching. I'll write D by F switching, and here it is V0. So here it is for buck converter. But I0 by V0 is 1 by R. So D by R into F switching, because I0 by V0 is 1 by R. So therefore this is for buck or circuit 1. For circuit 2, it is, what is for circuit 2? IC1 is I0 into D by F switching into we have to write VC in terms of V0. So VC is V0 by 1 minus D. So it is V0 by 1 minus D. So it is D into 1 minus D by FSW R. This is for buck boost or circuit number 2. Oh, I forgot the 2 actually. This should be 2. Yeah, it should be 2. I forgot the 2, and the 2 should be here, not here. So here it should be 2. And for boost it is I0 minus In, or I can write in terms of T off. So that is In. So In into 1 minus D by 2 F switching into V0 by 1 minus D. So it is 1 minus D whole square by 2 F switching R. This is for boost or circuit number 3. So we also find that the switch S2 is a single quadrant, that is S2 can be a diode D1. So S2 can be a diode because it just needs to block the voltage of one polarity, and it should pass current in only one direction. So that's why these are the basic topologies of DC-DC current converter. So what we can do is, we can now we have finished with we are done with the analysis of the DC-DC current converter. Now if you want to formulate higher order DC-DC voltage converters using these DC-DC current converters, what you should do is you should replace a voltage source with this cell. This we have to replace, and then we'll get higher order DC-DC voltage converters. We'll get higher order DC-DC voltage converters with different topologies. Just if we replace this with this, higher order or fourth order. Why fourth order? Because then in the circuit, so we'll be having two inductors and two capacitors. Why two capacitors? Because you have to replace this with this, and at the load add additional capacitor across R, that is C2. So replace a current source with a voltage source in series with inductance, and at the for parallel of R, in parallel of R, add another capacitance C2. So the capacitor which is already present in the DC-DC current converters, let that be C1, and then this inductor which is already present in this DC-DC current converters, let that be L2, and this inductor which you are adding in series with this voltage source, let that be L1. That's why it becomes fourth order, because here we have 2L and 2 capacitor. This will give rise to fourth order DC-DC converters. So two very famous topologies of DC-DC fourth order converters is, first is the Chuck converter or Chuck converter. Chuck converter is a voltage source, inductor L1, a switch S1, a capacitor Vc, then instead of S2 we have a diode D1, we have another inductor L2, and then we have a capacitor and a load. Another one is a SEPIC. SEPIC means single ended primary inductor converter. A SEPIC converter means you have a voltage source, then you have the input looks very similar to a Chuck converter, L1, S1, this is also C1 or C1, C2, but here instead of diode we have a L2, then we have a diode T1, C2. These are the famous fourth order DC-DC converters. So these are the following are the topologies of fourth order DC-DC voltage converters. Number 1 is Chuck, number 2 is SEPIC, and we'll get different other topologies also. So the other topologies are like a boost converter with LC filter at input side, boost converter with LC filter at the output side. So these are the various topologies possible. So we'll conclude this lecture here, and in the next lecture we will see the different possible topologies for fourth order DC-DC voltage converters, and after that we will start with isolated DC-DC converters. Thank you.